This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you for joining us for the Satellite Book Club Seminar Series. Another milestone today. This is session number 60. Hope everybody is having a good summer and everybody's staying well. We got a great presentation today. Note that this is a bit of a change from what was announced last week, but we're happy to have Chris Jackson, consultant scientist with the Satellite Oceanography and Climate Division, step in today with his presentation, Near Real-Time Tropical Cyclone Winds from Synthetic Aperture Radar. Our facilitator is Stephanie Stevenson, meteorologist and programmer with the Technology and Science branch of the National Hurricane Center. A few reminders before we get started that this session is being recorded. There will be an opportunity for Q&A after the presentation. Please post your questions in the chat and we will field them in the order they are asked there. We're always looking for future presenters, particularly from our field offices. So if you have an application you'd like to share with your colleagues, please reach out to us. We'd love to hear from you. The training team can help create training materials that may be unavailable or point you to materials that you may be unaware of. Brian Mata in the Office of the Chief Learning Officer can help regarding that. I'd just like to thank, as always, the Tower S team, particularly Kashad Bowman, the Office of the Chief Learning Officer, GOSAR and JPSS programs for their support of the Satellite Book Club. Without further ado, I'd like to introduce Christopher Jackson, who's currently a consultant scientist with the Synthetic Aperture Radar group in the Satellite Oceanography and Climate Division, where he works to develop products for various NOAA customers based on SAR imagery. He received his master's in applied physics from George Mason University in 1998, and for the last 30 years, he has conducted research into the use of synthetic aperture radar and optical sunglint imagery to study a variety of ocean-related phenomena, including sea surface winds, nonlinear internal waves, and sea ice. He also served as the editor of the Synthetic Aperture Radar Marine User's Manual, which was published by NOAA back in 2004. Chris, thanks for filling in today. We're glad to have you. I'm looking forward to your presentation.
All right. Yeah, thank you, Jordan. I'm really pleased to be here. I'm always happy to preach the SAR Bible, as it were, and it's been an exciting time in SAR science here with the advent of Sentinel that went up in 2014, RadarSat Constellation mission that went up in 2019, with NISAR on the horizon in 2022 or 2023. So the SAR applications are only going to continue to expand here as we move forward. The one I'm going to talk about here is the application that we put together for near real-time tropical cyclone winds. And I'm going to focus on the system, not so much the science of the synthetic aperture radar detection, but we'll get into a little bit of that. At the bottom left, the two spacecraft and the two sensors that we are going to use primarily for this, which is the RadarSat 2 satellite and the Sentinel-1, and I'll have more to say about them going forward. And on the right is a composite that we put together of all the SAR wind images we were able to generate from typhoons in the Western Pacific for 2018. So I want to start with a couple of pictures. My goal with these briefings is to move you sort of from the familiar to maybe the non-familiar. And here is a image that was taken nearly simultaneously with both Himawari 8 and RadarSat 2 of Super Typhoon Goni out in the Western Pacific last year. The Himawari 8 image is a visible band image collected at about 500-meter sampling. You can see some sun glint in the imagery. That was the sun was very low on the horizon. It was just coming up or rising during the Himawari collect. You can see a very clear inner and outer eye wall in the center. You can see some banding around the outer edge of the storm. And obviously, as an optical image, this is looking at the cloud tops. On the right-hand side, you see something very similar, but this is the RadarSat 2, and so what you're looking at is the radar backscatter from the ocean surface. So you can see, again, a very small, tight eye. Right outside the eye, you can see some attenuation due to rain banding. You can see the outer rain bands around the outer part of the image, and you can see some cyclonic streaks sort of here in the lower left as the wind is circling around the tropical cyclone. So again, you can see we get the same storm nearly at the same time, and there are a lot of different information that can be acquired from the two different scenes. Just a one slide background for those of you that may or may not be familiar with synthetic aperture radar. So SAR, like any microwave instrument, it works by transmitting a pulse and towards the ocean surface, it receives a reflection. It records both the amplitude and the phase. So it's a coherent sensor, unlike the scatterometer, the current generation of scatterometers. And that's important because it's that coherence that allows the image to actually be created. So that phase information is key to generating the SAR image. The latest generation of SARs that's been around for about the last 10 or 15 years are fairly sophisticated instruments. They have a variety of beam modes, ways to collect data. You can see on the left-hand side here, this is the Sentinel-1 imaging geometry. The radar looks off to the side from angles of roughly 20 degrees out to 49 degrees. In the left-hand side, you can see it collects in this interferometric wide mode, which is sort of a 3-beam position mode, covers 250 kilometers. We're also going to see data from, on the right there, this extra wide swath mode, which is a 5-beam position mode that allows us to cover roughly 400 kilometers. And getting those really large swaths is important for doing the tropical cyclone work because we can capture the eye and out back to sort of the normal winds, and so we get to capture the whole storm. Again, the SAR has the advantage here. You can get resolutions, very high resolutions, greater than 100 meters on swaths as wide as 500 meters. The latest generation of satellites has resolutions, sort of sub 3 meter. There's obviously trade-offs between the coverage area and the resolution. And again, we're going to use data from the RadarSat 2 and Sentinel spacecraft, which are all C-band systems with about a 5 centimeter wavelength on it. So again, the focus of the presentation here is the fact that we have put in place this fully automated system to produce high resolution, near real-time tropical cyclone winds from SAR. Again, we're relying on the Sentinel-1 and the RadarSat 2. We use the high resolution data on a wide swath, and we're going to use the cross polarization channel. So we're going to see data where the transmission is in vertical and the receive is in horizontal. It has a couple of different things. It's been shown to be insensitive to instance angle effects, and we can extract winds up to tropical cyclone strength here. The downside is that it's the scattering physics is a little bit different. It has a little bit of a volume scattering component, and so the signal to noise is very low, and noise removal is key to effectively using the cross polarization data. With this high resolution on a wide swath, we get to do a lot of good things for tropical cyclone characterization. We can produce radial wind profiles, which I'm going to talk about in a couple of different slides, which allows us to very accurately measure the maximum wind speed in the storm and determine the radius of maximum winds, which we know the forecasters are really interested in getting for characterization. We also go through and we find the 34, 50, and 64 knot wind radii, sort of the so-called quadrant fixes. And obviously, because we can resolve the eye very well, we can produce a very accurate eye location at the ocean surface and not at the cloud top. On the left-hand side here, we have an image from Typhoon Maysak back in 2020. This was a giant storm. Its radius of max winds, it was almost 80 kilometers. So ever since SAR has been put on orbit back in 1978 with the first civilian SAR CSAT mission, there's been an interest from the tropical community, to look at this. So this was an image again from Hurricane Iva back from 1978. It was a 100-kilometer swath, was CSAT swath with a 25-meter pixel, and again you can see all the classic characteristics that we are seeing in the current SAR imagery. We see the rain bands, we see the eye. But in order to exploit this, it's really only come into its own in the last few years. It's only in that time period that we've had the development of a cross-polarization geophysical model function that allows us to extract winds accurately at speeds greater than 25 meters per second. The data are readily available in near real time, and there has been active efforts to track and acquire tropical cyclones with RadarSat and Sentinel that have allowed us to build up a database to examine the imagery, and begin to do the science that allows us to exploit this imagery effectively. And we really have to give a shout out to the Copernicus Earth Observation Program, because they have played just a key role in making this possible. Obviously, they put up the Sentinel-1 spacecraft. There's 2 Sentinel-1 spacecraft. They put it through where it has a regular collection pattern. More important than that, they have allowed it to have a free and open data policy with near real-time delivery. I mean, it is just amazing with how this has opened up SAR data for use to support a whole variety of applications, to having this free and open data policy and near real-time delivery. And for the last few years, there's been a program inside of Copernicus in combination with IFREMER and our colleague Alexis Mouche to do a satellite hurricane observation campaign, which again has allowed us to collect a lot of storms to date. And I got a slide on that later on that allowed us to do the analysis and extract the good science that's allowing us to put this program together to support the forecasters currently. So again, sort of, why SAR for tropical cyclones? Well, it's pretty simple because we can observe the ocean surface at high resolutions. In this case, our products are typically less than 500 meters sampling spacing, and we can get accurate tropical cyclone winds for winds greater than 34 knots. And so this is just a very simple comparison. This is Hurricane Felicia from just about a week ago. We can see on the right, this is the ASCAT-A scatterometer results in copole, so it was a vertical transmit, vertical receive. And so you can sort of see the vague outlines of the storm there. It only returned a maximum wind speed of roughly 20 meters per second. This was a very compact storm with an eye diameter of only about 10 kilometers. And so you can see, using the SAR with its high resolution, we were able to resolve the eye very clearly. We were able to see the symmetric winds around the system very clearly. If you look at the data, the 500-meter product that we produced produced a maximum wind speed of almost 63 knots. If we do an average, which is sort of our version of a 1-minute sustained wind, we can see it was as high as 52 knots. And so this is why the forecasters and the researchers are really interested in SAR for this application. And so if you have that resolution, as I mentioned sort of in the early slide, well, what do you do with it? Again, you can characterize the storm very well. And so here we have the example of the profiles that we generate. On the lower right-hand side here is the northeast quadrant of the storm. The gray dots are the actual SAR pixels, so the wind speed for every SAR pixel that's there. The black line through the middle is the mean of that. The lines to either side are 1 standard deviation. And you can see as you follow along that profile, you can easily identify where the maximum wind speed takes place at about 24 nautical miles, here at almost 71 knots. And as you go down that profile, you can find the passage of where it is for the 64, 50, and 34 knot wind radii fixes that we produce. In the upper right, we've gone through and done that for all 4 quadrants. We go back and report that out in that little box there in the middle, since we have a very accurate location at the center of the storm. You can see for the 4 quadrants, we've listed the R34, 50, 64, the Vmax values, and then the Vmax and the Rmax. The lower left-hand corner is a contour plot that shows the 34 knot winds in gray, and the arcs are our fixes that we have derived, overlaid to show how well that they represent the storm characterization. And so this has been key for researchers and has excited the forecasters. So how do we go about producing that picture? And so this is basically our system that's set up here at STAR. And so we have an automated data acquisition process. And so the system goes out and looks at the BDEC and the NOAA SAB for active storms. It extracts the estimated position of where those storm centers are, and then goes out to the Copernicus data hub and looks to see if there are any data that are over that storm that have been collected as part of an incidental collection. For RadarSat-2, we schedule those collections, and I'm going to talk about that in slides coming up. And so we can simply let the system know when it needs to expect to get those data in. So the first thing it does is it goes through and it creates that 2-dimensional wind speed map of the ocean surface that I've been showing to date. It determines whether the eye estimate is in the scene or close to the scene, and if it's in those situations, it will goes through an algorithm and produces a refined storm center location that it reports back. It uses that to then derive those products that I showed on the previous plot, the radial wind plots on the quadrant basis. We produce an ATCF radial text file. We produce the 3-kilometer net CDF files, and I'll talk about these products going forward. And we send that data out to both the ATCF system for use by NRL and the Joint Typhoon Warning Center, and AWIPS, which is work we've just been doing with Lee Byerly and the National Hurricane Center to get this available down there. So again, it's sort of on the right is sort of the system block diagram. The data have a latency, anywhere between 1 to 3 hours. We're seeing the Copernicus data on a sort of a 3 to 6 hour latency. It's been improving over the last few years, particularly for tropical cyclone collects. They seem to have a way to sort of push them to the top of the queue. RadarSat, because we task the satellite directly, we can get latencies as low as 1 hour, particularly for places in the Atlantic where the spacecraft is going to go over a Canadian ground station almost immediately after collection. The data come into STAR. It takes us about 30 to 45 minutes to produce all of those products. We push the data out to the STAR FTP site. It goes out to our web page, which I'll talk about in another couple of slides. From the FTP site, it goes into AWIPS. We also send it again out to NRL on the West Coast, who will inject it into ATCF. And from some there, and with AWIPS, it gets out to the forecast offices. So this is the STAR tropical cyclone webpage that we put to support these observations. The URL is at the bottom. I keep begging for a short URL, and hopefully someday in the future we'll get it. You can see we put out the wind speed map. We put out a contour map. You have access to the data from the 4 quadrants. If you look in the lower left-hand side, there's the PNG, there's a KMZ, there's the normalized radar cross-section image if you want to look at that. The net CDF files are available with the wind and cross-section information in it. There's the ATC text file that's out there, and then there's another text file that just simply describes the radial winds. One of the new developments this year is the work we've done with Lee and Tower S to support National Hurricane Center, and that's getting these data into the AWIP system. And here's an example of that from Hurricane Laura in 2020. And so in the upper left-hand side is our PNG picture. Overlaid is the same image there with, it looks like the channel, the GOES IR channel. And so you can see we've sort of split the eye, and you can see the difference between where the high-speed winds are and the IR signature that comes back. And again, we worked very closely with Buck Sampson at NRL's in Monterey to get this data into ATCF to support Joint Typhoon Warning Center. And so here's an example of an ATCF output showing Typhoon Babi from last year, August of last year, with the ATCF text file there sort of at the bottom. And again, as we've noted going forward, we've developed this product, and one of the keys has been is to how to package this data effectively to get it out to the researchers so that they can get it integrated into their workflows, because we know there's a lot of data that they look at, and it needs to be effectively put into their system so that they can access it relatively easily. So I kind of showed you all the positive aspects of the SAR, the high resolution, what we can extract from the storm. There is a little bit of a price for this. And so the advantage of the SAR is that it collects the data the way it collects in terms of swath and sample spacing. The downside is if you're going to collect that much data, you can't collect it everywhere. And so it's limited in its footprint on any given day. Unlike the scatterometer that can cover all the world's oceans on any given, every day. So the SAR is limited. And so you can see here on the right is a picture of the Sentinel-1 spacecraft. It collects roughly 600 scenes a day over both the land and the water. So roughly 25 minutes of every orbit is used to collect this imagery. Sentinel-1 has this standard pattern integrated into it, which is nice for repeatability. And so we know it's going to come in every day. They publish what they're going to what their future collections are. And in addition to this standard collection pattern, there's obviously special collections that are put in place on a regular basis to either support tropical cyclones or the disaster charter or what have you. As part of the Sentinel-1 regular collection pattern, we do sometimes fortuitously acquire this tropical cyclone imagery, usually when it's close to land. And this is why that system is constantly checking the VDEC data and the SAB outputs to look for those eye locations and see if there have been any fortuitous collections in the system. And if it finds them, it goes out and grabs them and brings them down. Other than that, tropical cyclone coverage is the result of active programming. So you have to get an idea for where the tropical cyclone is. Again, there's sort of 4 conditions here. We need a forecast track. The storm has to persist long enough for the collection to be scheduled and take place. Obviously, the location and timing of the SAR footprint has to align with the eye and track location. And so sometimes that limits us to only a few collection opportunities on a given storm. And the programming of the spacecraft need to be done usually 2 to 5 days in advance. Obviously, the closer that we can get to the time of collection, the more confident we can be as to whether we're going to get an eye hit or not. And so let's talk about that here on the next slide. And so the RadarSat 2 acquisition planning is done by STAR, myself, Tyler Ruff, and Jesse Torres. I should have introduced as our collaborators here at the beginning of the briefing. We're doing it in conjunction with some other our U.S. government partners and MDA Space. MDA Space operates and owns the spacecraft. We're doing it in STAR on our best effort basis. We're hoping we can get this institutionalized here going forward. The Sentinel spacecraft are programmed up under the Copernicus Cyclone Monitoring Service. So experts at IFREMER coordinate with ESA to put those collections together. We do our best to coordinate with Alex Moosh, who, again, another colleague who is responsible for doing those collections. Copernicus has an effort to sort of operationalize their tropical cyclone collections, so they're continuing to elevate that. It started out as doing some basic science, but they want to move it up to a Copernicus service. But here in the US, again, the RadarSat 2 spacecraft is the one that we have access to, and it's the only SAR that's currently on orbit that we can task directly to support tropical cyclones. And our goal, both with Sentinel and RadarSat, and again in connection with Alex, is to acquire as many of these tropical cyclones as possible going forward. We've kind of got the forecasters interested, and now we need to make sure that we follow through and can get the data they need. And so we started to do cyclone chasing here in earnest sort of in the July of 2020, and you can see for the second half of 2020 we collected 16 tropical cyclones, a total of 45 scenes on approximately 27 dates from a variety of basins over a variety of storms. So in the Western Pacific, the Atlantic, the Gulf of Mexico. And then this year we started early. We started actually in December of 2020 chasing Southern Hemisphere storms. And so to date, we've gotten 13 cyclones, collected approximately 23 scenes over approximately 19 dates. And so those are the ones that we have actively programmed and we're able to acquire to support the work here. So, we didn't do this in isolation. We knew what the SAR was capable of. We needed to sort of sell it to the community, for lack of a better term. We needed to get forecasters interested. And one of the groups that was willing to work with us early on and provided us some great feedback has been the Joint Typhoon Warning Center. And so we want to thank Brian Stahl, who's the director out there, Brian Howell, one of the forecasters, Buck Sampson at NRL, who sort of are the interface, and John Knapp at STAR, who's done a tremendous job in helping us to package this data up, make it available, help us to explain to the forecasters what it can do for them, and we've had some great acceptance out there. So we started in 2018. We sort of just introduced it to them. 2019 was kind of the getting to know the products and the capabilities a little bit better. And by the end of 2020, they were able to put this to support their operational forecasters, and we were getting great questions back as to when we can deliver it, and if they saw something that sort of looked anomalous. It was great. You know, we went from the situation where if the SAR didn't quite match what they were getting out of the Dvorak technique or some of their other sensors, and they originally were sort of writing it off to maybe there was a problem with the SAR, and by the end of it now, their confidence in the SAR measurement, and they're beginning to go back and sort of question maybe some of the understanding of what was going on at the time. And so this has been just great. We presented our results here at the conference that took place in April 2021, and we received some really good product feedback from the community at that point. So we had a great relationship with Typhoon Warning Center. We have been actively working this year to engage National Hurricane Center and Central Pacific Hurricane Center. And so we really want to compliment Mike Brennan and Stephanie and Thomas there. We've had some great meetings earlier on this year to figure out how to get this data to them this season. Lee Byerly's been key to that. And so he's worked really hard beginning of this year to get these NetCDF files that we produce into AWIPS to support NHC and TPHC. And we just sort of had our first realization of that here with Hurricane Felicia a couple of weeks ago, provided the test where NHC had a chance to look at this stuff in near real time and provided useful feedback to us. And we were really pleased to see the reference to the SAR in one of their forecasts that went out, forecast discussions, the internal forecast discussions that took place. And so we're really excited going forward here in 2021 that we're going to be able to do some really nice things as the Atlantic hurricane season heats up. So this is our archive that we have available, roughly broken down by year. And so you can see we've collected data on over 180 storms, 187 storms on roughly 500 dates with about 288 eye hits. And so there's a large data repository to be mined by researchers. We do it ourselves for the product development. And all of these collections and the NetCDF files associated with them are available on our website. And if there's any questions or we need to package anything up specifically for you, let us know. But you should be able to go out there to that site and click through. It's broken down on a per year basis. You can select the storm of interest, and then once you bring that storm up, it'll show you all the SAR collections for that storm. You can go through and look at the imagery. So I want to just take, this was the image on the right is a composite from the 2019-2020 Atlantic hurricane season. Again, a wide variety of storms from nice high wind, small eye to these storms that are transitioning into the extratropical, where you get what we call these galaxy arm. We've nicknamed it sort of these galaxy arm features. So I'm going to now just go ahead and I want to highlight two collections that we were really pleased with over the last year. One was this Hurricane Marie in the Eastern Pacific back in October. And we had an opportunity to get 5 eye hits in 4 days on this storm. And so it actually starts in the lower right-hand corner with our first collect when the storm was only 61 knots on October 1st. And it's set up geographically so the storm was moving from east to west, which is why the images are laid out the way they are. And so we came in the next day, we got to watch it intensify with the RADARSat-2 spacecraft here at 69 knots. By that point, it had persisted long enough that the Sentinel had been programmed up, and so we got a hit very close to maximum winds there on October 3rd. We hit 110 knots, and we watched it gradually decrease in strength over the next couple of days out to October 4th. So this is one of our really nice collects. We were able to watch the evolution of the eye and the winds in the SAR. And we had a even better opportunity earlier this year in the Western Pacific with typhoon, may have even gotten to be super typhoon Surrogate, where we managed to get 5 eye hits in 60 hours. I mean, this was just, the data were coming fast and furious, and the forecasters out at Joint Typhoon Warning Center were sort of in their glory out there with this kind of stuff. And so, if the storm tracks right and it persists long enough, we can do some really nice collections with these systems. So that's everything I have specifically on the tropical cyclone program. I have 2 slides just to sort of put this in a little bit of context. Again, the program didn't grow out of just sort of grow out of the ether. It came out of a larger SAR ocean surface winds derived ocean surface winds product that we produce in SAR for SAR in general. And so this product is actually in operations at OSPO and has been in operations at OSPO since 2014 with the RADARSAT-2 spacecraft, and it was expanded in 2016 with the Sentinel spacecraft. It's going to expand again here in 2022 when the RADARSAT Constellation mission data are integrated into it. The focus is on the US EEZ for both Alaska, the CONUS, obviously Alaska, Hawaii, and the US territories, and we've expanded it to include the Caribbean and the North Atlantic. We get the near real-time data with somewhere between 4 to 10 hours latency. We can extract the wind information right up to the coastline, produce the data in a variety of formats for folks to use. Again, the goal here is to get the WFOs sort of hooked on it. We've been working with Lee and Tower S to make this available to some of those forecast offices. I know we've just had a really nice interaction with the group that does American Samoa. For some reason, RCM was giving us a really nice collection over American Samoa for a couple of months. The people in Alaska are interested for the reasons that you can kind of see in the image on the right, that we can resolve the gap flow winds up there that are important to their local forecasts. And again, you know, sort of a shout out to the Alaska Weather Service and the Alaska Sea Ice Service, who have been supportive of the SAR efforts for 20 years. They were one of the groups that helped get this into operations in OSPO. And so we're glad that we're now finally able to provide enough imagery for them that sort of that wait has been worthwhile. And it's only going to get better here. In March 2021, NOAA finally became a vetted user for the RADARSAT Constellation mission. And so we've got almost double the amount of SAR data that we had coming in with Sentinel-1 coming in. It's the same amount with Sentinel-1 that we do with RADARSAT Constellation mission. So we've doubled the amount of SAR data that coming in. We've got some improved coverage of the area around Alaska. We're seeing really nice collections in the North Pacific and the North Atlantic along the Canadian coasts because it's focused, it's sort of North America, Canadian waters focused. And so we finally have something to offer sort of maybe the OPC people going forward here, because we're seeing daily coverage of those spots in the Atlantic and the Pacific Ocean.
Chris, hope you're planning to wrap up in the next few minutes. I know people have to drop off and we got quite a few questions to get through as well.
I'm on my last 2 slides.
Okay, thank you.
Just one other point, you know, again, with the resolution, you can do things other than winds. This is an example of a SAR wave, ocean swell waves that we were able to resolve under Hurricane Hagibis. It has about a 400-meter swell width, and you can see the nice pattern there over the wind over near the islands. And then sort of some final notes. So we do have an email distribution list. If you want to know when the tropical cyclone collections are planned and acquired, just pass along your email address. This is only going to get better going forward. We got additional satellites coming online. As I said, RCM Sentinel-1C is going to go up in 2022, early 2023. We have NASA's NISAR expected to come down the line in 2023. If you're interested in further discussions or more details of the products or the delivery, not only of the hurricane, but of the ocean surface winds, we're also doing flood and inundation mapping. We've got oil spill mapping. We've got sea ice work. And then the only other thing, you know, where I put this out here just for some advocacy purposes, is that the operational side of the house of NESDIS, the OSPO side of the house, they want to retire RADARSAT-2 from the production stream. It's still going to be available through STAR, but if we want to institutionalize this, we need to get them to change this decision, and because it's going to affect the amount of cyclones we can put through the actual system that's been deployed to OSPO. And then finally, just for your reading pleasure, we just got a paper published in EOS just about 2 months ago here that's on this topic exactly. So if you just Google search EOS chasing cyclones, it'll come up as your first hit, and you can have sort of a document that describes a lot of the things that I just described in this briefing today. And there's one other slide here that we can make available, but just is the websites where you can get access to the tropical website and the regular SAR winds, and then in addition to some other data sources, the ESA Copernicus and the Canadian RADARSAT Constellation mission. that's everything that I have. I appreciate the time, and looks like I ran a little long, and I'm sorry about that.
Thanks, Chris, for that presentation. I want to encourage everyone to stay around for the discussion that we're going to have, and also complete the feedback survey posted in the chat room by Lee just now. Just to mention, next week, a week from today, on Thursday, August 5th at noon Eastern Time, Rebecca Smiley and Jeff Skudzinski from NASA Sport will discuss satellite soundings via open source tools for situational awareness. I also want to encourage attendees to contact the Tower S team, Lee Byerly and Kashad Bowman, for questions about the SBC or for configuration of satellite products. More information will follow in an email from the Tower S team. I'm seeing a lot of good questions rolling in through the chat box here, so we'll go ahead and get into some of those now. The first one I have here is from Mark DiMaria. If you had unlimited access to the 2 satellites and perfect track forecasts, what is the maximum number of overpasses you could get per day for an individual tropical cyclone, taking into account the swath width?
Oh, I got to do math to get that, Mark. You know, we'd probably be able to get, you know, the cyclone maybe 2 out of every 3 days, if we had unlimited resources here. But you know, it kind of depends, and that's assuming we've got the 500-kilometer swath with. You know, unfortunately, probably the perfect tropical cyclone system that was available was the NASA SWAT. Somebody help me out here. The active passive mission that went up in 2015. It had a 1-kilometer SAR on it that covered the ocean daily, and so I mean we could have seen everything. But unfortunately, they lost the active SMAP. We lost the active transmitter after only 100 days. So if someone will give us $1 billion, we can put up a 1-kilometer SAR and we can get cyclone coverage daily. But with the current sensors, you have maybe 2 out of every 3 days, maybe 2 out of every 4 days. But we do much better than we're doing now if we had more resources, certainly.
All right, we have 2 other kind of related questions. One from Bill Schulberg. And another from Joe Phillips asking if SAR imagery can be tasked for other purposes. So Bill mentioned flood areas, and Joe is asking about things like Great Lake fall storms when the tropics are quiet.
Yeah, we should be able to. We'll talk about that. So there's a maybe it needs to be a larger discussion. So SAB has been working to task some of the newer generation X-band satellites. The relationship we currently have to do RadarSat with NGA has some limitations, but you know, money solves this problem. And for example, Ice Center has in place contract with RadarSat 2 directly, and they can task whatever they need to. So yeah, it comes down to resources available for it, but we can talk more about that offline. I think there's an effort inside NOAA to acquire some data from some of these newer sensors, which may be more suited to the tasks of flooding over small areas or areas of the Great Lakes that don't require sort of these 500-kilometer swath type things. But we have a flooding effort in place we can talk about offline too.
All right, the next question from Michael Jimolkowski. Assuming the SARs are fairly powerful active sensors, can or do their satellites accommodate any other sensors?
And so in the past, there have been multiple sensors on these satellites. CSAT contained both a scatterometer and an altimeter. The RadarSat Constellation mission actually has AIS on it, but for the most part, the trend has been to make them dedicated SAR systems. NVSat had both a scatterometer and a SAR on it when it was up for a time. So it sort of depends on how the engineers decide to configure it. But the current generation of systems have been just dedicated SARs.
Okay, and then more of an operational question here. In the future, do you know if WFOs will have access to SAR data sets and AWIPs? I know there's ongoing efforts with like the national centers, as you mentioned, and I think you touched a little bit on some of the WFOs.
Yeah, so our goal is to get it into them. We've been working with Lee, and he's been working hard to help us out. Again, we've had interest expressed from Alaska. Obviously, the national centers The American Samoa people were interested earlier this year. We make these NetCDF files available. There's a way to ingest them into AWIPS that has been worked out. There's a couple of methods. There's Lee's, where he does the ingestion automatically, but in addition to that, the folks out in Wisconsin, John Neff, have worked out ways to ingest our NetCDF files directly, and if there's something of interest, we can make those available like we do for some of the people that are already using it, and we can teach you how to do that.
Okay. I'm not seeing any more questions in the chat box, but maybe one that I have is, what is the typical lifespan of a SAR instrument?
So yeah, they're fairly long-lived once you get them up and working. So RadarSat 2 has been up since 2008. It's still working well. RadarSat 1 lasted 15 to 17 years. NBSat lasted over a decade. The ERS systems lasted almost 20 years. And so we expect the Sentinel spacecraft, to last on that order of, 15 years-ish. Yeah, they tend to be long-lived missions.
All right, great discussion there, and I'm not seeing any other questions come in the chat room, and we're coming up on 45 minutes, so maybe I'll toss it back to Jordan now for some closing remarks.
Thank you so much, Chris, and thank you, Stephanie, for moderating today. I just do have one question before we adjourn is, what can be done about tasking SAR, very early in the TC formation? Is there any particular invests that you're looking for, or who is doing that and how is that done?
Yeah, so Tyler and I are doing that, and we've had those similar requests from Hurricane Center earlier this year. We need a location and a time, and then if you give us those two coordinates, we can check to see what the coverage is for RadarSat 2, and if necessary, we can try to get down a scene. But so we need the coordinate and what time period that coordinate is valid for, and we can try to do that if there's interest to do that.
Okay. Well, thank you so much once again for your presentation today, and thanks for our audience members for all the great questions. Really appreciate the participation. Just as a reminder before we adjourn that, again, a week from today, Thursday, August 5th, we will have a presentation on satellite soundings via open source tools for situational awareness, so I hope you'll join us. Until then, please contact TowerS team for questions about the Satellite Book Club, or if you have any needs related to configuring satellite products in AWIPS. TowerS team, Kashad Bowman, Lee Byerly standing by. Hope everybody's summer's going well. Hope everybody's staying well, and you will be back here next week. Take care. Thanks, everybody.